All right. So let's talk. We're going to talk about regression again tonight. And then, so the lab for this should be due this week. I will start grading project proposals tomorrow. I didn't quite get to it today, so sorry about that. That's my fault. I won't blame. I told Angela I would do the proposals. She's chugging along on the labs, so we'll get you guys some feedback. But I do want to say a couple of things. Is I'll put this post here again. I updated the link on the project page was wrong until yesterday. But here it is again to sign up for your time slot. And then I also wanted to point out, I put here, if you go to GitHub or you just follow this link when this, actually I posted the slides earlier, but so there's some files here. There's an example project slide. If you download this file, this is what it looks like. I'm not gonna quite do it, but I wanted to give you at least like some kind of idea or template. And I used, I have my own template I use obviously for classes. This is sort of the built-in IO slides. So if you want to use R Markdown to build your slide deck, this is one to use. You can look at the oh shoot, I should have left this open. I closed that tab. But if you look at this RMD file, you can use this as an example. So this one would be doing regression. So kind of some of the key highlights of, I call this hanging chads. So I have some background on this data analysis. I'm going to go through a different regression one, but this is looking at election. Since it's election season, I thought it was relevant, but this is looking at votes in Florida in 2000. And if you weren't, I don't know, I remember this very clearly. This is the year where George W. Bush won, and it, even though Al Gore actually had higher popular vote, it really came down to one county in Florida that turned, that kind of had caused the results of the presidential election, and really comes down to this Miami-Dade County here that I highlighted here in blue. And so there's this data set here called elections that has number of votes for Bush and Buchanan. So there was a third party candidate that year. And if we plot like the sort of the relationship between the Bush and Buchanan, we see tends to be a pretty, close relationship. So between those two, with the exception of this one dot up here. And if you run just a simple Pearson's correlation on these two values, this is, by the way, by county, I should say, right? We can see the correlation is 0.625. But we have this potential outlier up here. And okay, so then I ran a linear regression that shows that indeed it is, there's a predictor, and knowing the Bush predicting Buchanan, we get an R squared of about 39%. We look at the residuals, and then when we check our assumptions, we see a couple of problems, right? One is we have this one county way up here. It also shows up in the fit and residuals. We look at the QQ plot, which generally looks pretty good, but then we get this one point that is way off. And then, of course, that one outlier really skews the distribution of the residual. So obviously we have some assumption problems. So of course we could try to do a log transformation, right? And that's what I did here. So we see that county kind of brings it down a little bit when we take the, we do a log transformation in both directions. When we do that, the correlation increases to 0.92, which results in an R squared of 85%, which is pretty large in almost any context. But if we remove that Palm Beach without, we get a R squared of 86%, which is actually a little bit higher. Looking at the residual plots of the logs definitely makes things better, which is good for our assumptions. But if we sort of take the log transform or obtain a predicted value for Palm Beach, given the model fit without, we would get a predicted value of 2,809, right? Which is a difference of 3,407. Right. And this difference, this error here is particularly interesting and meaningful, because those votes are that difference in the predicted value is bigger than the margin between Bush and Gore in that particular county. Anyways, just a little history lesson. It comes down to where the problem occurred is that some people voted for, because of the way that their voting system. This is, at least for me in New York, for a long time we had levers until just a few years ago, and now we have those paper ballots where you fill in the dots. But here you had to punch these holes. And so I don't know if you heard about the hanging Chad issues. A lot of that was because of the way that the butterfly thing was set up. People were voting for Buchanan, who probably thought they were voting for Gore, and so some of the votes kind of got misaligned. So, anyways, some simple regression models could have kind of helped here. But overall, the point here is just to kind of give you a sense of how I structured the project, right? A little bit of an introduction, some analysis, a little bit of information about your variables, and references if you have them, and then some kind of conclusion. Actually, my conclusion could be better, quite frankly. But so is there questions about this, at least in the structure? Now, this is a regression example. Some of you may end up doing null hypothesis tests. Depends on your data set. Any kind of procedure that we talked about this class is completely fine. And if you want to be ambitious or read ahead or wait, we are going to do multiple regression next week. So you get a sense of that. And then we will do logistic regression just before Thanksgiving. So hopefully there should be time to do that. If you find that might be a better approach and you want to revise, let us know. So just think about multiple regression is going to be a situation where we have more than one dependent variable. And then logistic regression is going to be the situation if you want to run a regression where your outcome variable or your dependent variable is dichotomized. It's either like yes or no or true or false or something like that. So if that's something you're thinking about, we'll cover that in the next 2 weeks. Those are models that you could kind of include to your repertoire.
In terms of the feedback you're going to give, like, I guess I listed 2 things like as a mean group difference, but I guess my initial thought was to do regression. Like, I just wrote it all, I guess, because you said it's somewhat fluid in the sense you don't have a formal, but I guess in terms of feedback, like, are you going to give like, oh, like maybe you should think about this, or more of like you just kind of what you should do.
Also, I can do multiple models, right? Because at first, the way I thought it, I'll do a confidence interval, but I could also put in, I could also do linear regression, right? If it applies, and then you'll give feedback, because I'm afraid maybe mine was it was similar to your example. Maybe it's a little too short. So you'll feedback if I need to change it, or I want to include several models to see if I understand where they're applied. Thank you so much. I just needed to know that.
Yeah. I'm sorry. I wanted to get started. I'll definitely get it before next Wednesday. I'll get through everybody who submitted on Blackboard. And then I can answer more questions, and we can set up meetings if you have further follow-up. A lot of times a good chunk of you might just be, looks great, keep going. But yeah, if you embedded questions in there, we can, I'll address those. And Angela's comment that if you want to, if we didn't say this, if you don't get 5 out of 5, then you can always resubmit for full credit. Like if something's missing or just doesn't look, I suggest some revisions. Sometimes I'll suggest revisions and still give you the full credit, because it might be minor and it's just sort of for the project. You might want to do that, but you meet the requirements for the proposal. Sometimes, I'll give you like a 3 out of 5 and just say, just resubmit and add what you're missing. So anyways, in the next week, you'll get that. Okay, cool. So we're going to talk about the questions here, and the questions you have, hopefully we'll get addressed some more, but do chime up and bring them in. So tonight we're just going to go through another example of regression and introduce a few other kind of, I would say, kind of ancillary concepts to regression of other ways you can do it. And this is actually some analysis I did many years ago. I guess it would have been 2013 or 14 that I did this. And I like it because it will allow me to introduce a few other things, but also kind of go through a real data set that's a little bit messy, some assumptions that we may have problems with, and kind of in practice how I handle some of this. So this is looking at, so if you're in New York State, by the way, if you're in New York and you care about New York and New York City has a fantastic open data website that you can just get all sorts of stuff. Like if you're thinking about capstone projects, so I always do New York City open data, because I can't remember the URL. I mean, you can just search, and there's so much stuff here, from education to environment to to economics, to police numbers, policing and arrests and murders and that kind of stuff. So worth checking out, and particularly if it's something local to you. You are at a CUNY school after all, but I know not everybody's in New York. So this actually comes from New York State, not from the New York City, and this is looking at so the report card data provides data on schools across the entire state. And one thing we were particularly interested is in 2013, New York State realigned the assessments to what's called a Common Core standards, which is a new way of just aligning curriculum. And if you're around or you're paying attention, this made a lot of news in the New York Times and basically every paper that covered New York State, that there was sort of a very large drop from 2012 to 2013 that kind of coincided with this. And some of the headlines were kind of, sensational in that they're like, students don't know anything, and, schools are failing. And so we kind of want to explore this a little bit more. And then I'm also not much anymore, but my dissertation had to do with charter schools and traditional public schools. And so I had some interest in how charter schools performed relative to public schools, in particular, in the context that one criticism often levied against charter schools is that some of them really teach the test. And I should say there a little bit of clarification, because there's subtlety in the language. There's oftentimes teaching to the test, and presuming tests are designed to cover what you should learn. Teaching to it is not necessarily a bad thing in my view, right? Assuming that the test is representative of what should be learned in terms of learning outcomes. Teaching the test is a little bit problematic. So that's like teaching skills on how you take a test and how you figure out which answer to guess when you know nothing about the question. I think that's, kind of problematic because you're not actually learning. Okay, so those sort of my two research questions is, first is, did the passing rates drop in a predictable manner? Because if you realign the curriculum, or if you realign the assessment, and particularly realign the assessment without actually realigning the curriculum at the same time, which was a major problem, then we might expect them to drop predictably. And was there a difference between charter and traditional public schools in sense of that dropping? So if we look at it, there's 1,362 observations in this data set. Each row is a school. So we're looking at school level data. So we could see, because I'm just looking at the first three, we have Albany schools, and we have things like number of tested, mean score in 2012, the pass percent that passed in 2012. We have a charter school indicator. Then we have some subjects and some other stuff, and then same set of values for 2013. So that's the kind of data we're looking at. And if we just look at the summaries on passing, so this is percent passing within each school. So in 2012, 61.73% of students passed, quote unquote, passed according to the criteria developed. And then in 2013, the passing rate was 22%. So fairly substantial decrease. If we look at the histograms, we see a couple of issues, right? 2012 is a little bit skewed. In practice, I probably wouldn't be terribly worried about this level of skewness, but there's some there. 2013 is a bit more problematic, right? They're highly positively skewed. So some things I'm going to try to do, right? So one classic approach when you have skewness like this kind of skewness is pretty common if you're dealing with financial data, or if you're in the finance world, very often you see distributions like this. So a log transformation is, one way to do it. Now, note, I actually have to add 1 to the pass rate because I actually have some schools with 0% of students passing, and the log of 0 is undefined. So in order for the log transformation to work, I have to add that 1, which is fine. It's a simple scalar. And so we see that I still have some issues. The distribution is a little bit better, but again, because we had 0 passing rates, we kind of have this floor effect, and actually this kind of bump up at the bottom, which is kind of unfortunate. So it helps. It's not perfect, but it's better. And sort of one of my approaches when doing regression, when you encounter situations like this and you're checking your assumptions, is well, you're gonna see a couple of strategies, but one is just to be transparent here, right? So we're gonna have some problems. In addition to doing what I would do here in terms of just doing regression, I'd probably try to use a non-parametric method like a classification tree or a regression tree or something like that. But that's something we unfortunately can't talk about in this course, but hopefully sometime in the program you would do that. And I think that conversation came up last week. Someone was asking, like, in practice, like, multiple methods often help me determine whether or not how badly am I violating the assumptions of this regression model? Well, let me see if I get the same answer using a model that doesn't have the same assumptions. So anyways, of course, let's plot our data. So part of that skewness, right? Some of it is just in terms of that floor effect, we had everyone drop. The other is to me, looks like there's a nice relationship, but I'm not sure it's a straight line. And so we'll address that as we go through. But so we're going to, so I'm saying all this to say, yeah, we have some problems, but I'm going to move on anyways, right? So I don't see particular issues here that are going to cause me to make assumptions that are sort of inflating any conclusions, right? So these particular assumption violations are going to sort of penalize. As we're going to see, my R-squared is going to be a little bit lower than if I actually do it correctly. So that's another thing I consider, is like my estimates are probably going to be a little bit more conservative than if I actually could fix all of these assumptions. So that's another thing to consider as you're going through. All right. Oh, and here's the scatter plot with the log transformation, which would be absolutely better particularly if I eliminated any of the schools that had a passing percent in 2013 of 0. It looks great. It's just this bottom row here that kind of causes some issues. So first thing, right? I'm just going to look at the correlation between these two, and I'm not sure if we talked about this function specifically, but the core.test. I think we might have just looked at core, which gives you the correlation. Core.test gives you the correlation, but then also gives us a 95% confidence interval, which is super handy for reasons I think we already talked about. It also tells us if it's, whether or not right, because we get a t statistic for that and a p-value. So we could see, so in this case, it's testing whether or not the correlation is different than 0. That's what this test is going to be doing, and gives us the sort of estimate, or which is going to essentially be the center of this confidence interval. Yeah, Christian.
Could you clarify something? Are you trying to look at the relationship between if they passed in 2012 and 2013? So like if they passed in 2012, are they more likely to pass in 2013?
Yes, that's right. Yeah. So because the correlation is fairly large, yeah, those who passed in 2012 are highly are likely to well, actually, no. I'm sorry. All the correlation is saying is that there is a relationship between the 2012 and the 2013, right? And so if we consider, this is percent passing. So we could say is, so in this case, because literally every school dropped in terms of the percent of students, but they kind of dropped in a predictable fashion. Right. So we're gonna try to draw a regression line here, right? So that we can kind of, if we knew what the 2012 passing rate is, we could fairly accurately predict what percent of students in that school would have passed in 2013. So it's really just the relationship between that percentage of passing in the 2 years that we're saying. So if you had a lot passing in relatively high passing rate in 2012, you would be among the top in the 2013, right? But it's not, yeah. So it's the prediction is going to come from, well, if I know the 2012 passing rate, and once we can draw that line, I can go up and say, well, here's what I would predict for that school. What percent of students would pass in 2013?
Makes sense. Thanks,
Does that make
Professor.
sense? Yeah, no problem. Okay.
How does the core dot test work? Like, is it like a bag sampling, or because I would think normally correlation includes all the points. So what is it actually doing in that function?
So it's calculating the correlation in the same way we did a couple of weeks ago, right? So we're going to look at the covariance and the ratio of the covariance to the product of the variances. Okay, the second piece it's doing is, so now you have a point estimate, and it's going to do a null hypothesis test based upon the sample size, and the null hypothesis is that the correlation is 0. Okay, so that's the null in this case. So when we're doing this t-test, we're doing a t-test that our point estimate 0.78 is minus the null, and in that case is 0 divided by I think it's gonna be n-1, right? And so that's going to come from a normal distribution. So that's what that is. So this t and these well, the t statistic is testing whether or not the correlation, it says it right here. So the alternative hypothesis, the true correlation is not equal to 0, right? So it's going to tell you, in this case, it's telling you what you should accept the alternative, right? And then the 95% confidence interval is telling us that from a sampling distribution, right? If we had a lot of samples here, that the true correlation, we're 95% sure the true correlation is somewhere between 0.7667 and 0.807, right? So those are reasonable places where that correlation. Does that help, Josh?
Yeah, no, I guess I'm just wondering, like, if you had a pretty strong correlation like this, like, you would test it more to get a sense of range of acceptable values, because it's, I mean, I would think it's definitely like the null hypothesis is not true in this case.
Right. And when you have a correlation this large, even with small sample sizes, it's probably going to be significant. But with smaller sample sizes, like correlations of, like, say 0.2, sometimes will be significant and sometimes will not. And right, because the denominator in that standard error calculation is n-1, right? So n has a big impact on that test statistic, right? And then from the test statistic is where you're going to get the p-value and calculate the confidence range. So yeah, 0.78 is obviously going to be statistically significant in even small sample sizes. Now, this raises something I didn't plan to talk about. But I think this question came up a couple of weeks ago. This is technically a population, because we have every school in New York State, right? But we still tend to calculate these confidence intervals just to kind of get a sense of where it is, because there are other sort of measurement noises in the like that may be present. All right. So here's another example why we care about such assumptions, right? So if I just use the raw metrics, I get a correlation of 0.79, call it, if I round it. But if I do the log transformation, or specifically, I didn't bother doing a log transformation on 2012 because that wasn't too bad. So I'm just looking at the correlation between past 2012 and the log of passing in 2013. I increased my correlation to 0.84. So that's like more than 5%, or 0.05, right? And when we look at the R-squareds, it's going to tell us that we're going to account for more of that variance. So again, this is like one of those situations where This is easier to interpret. And if I'm trying to do this analysis for more lay people or policymakers, this is probably what I would end up reporting, knowing that I satisfy myself that the correct thing is, what I mean when I say this is a conservative estimate is that this correlation in this example is smaller than this, right? And so this may be the correlation, but I might report something slightly smaller. But that you got to know your context, your domain, and your audience, because I probably would have this sort of in an appendix saying, well, doing the correct thing results in something like that. So moving on to the regression, right? So I'm going to predict 2013 passing rates from 2012 from this data set. And so we get, right, so remember this is our slope, here's our intercept, and we end up with an R squared of 62%. If we use the log, I get an R squared of 70%, right? So that shouldn't be a surprise because that's directly related to the correlation. So going back to our original question is, did the passing rates drop in a predictable manner? And the answer is absolutely, right? We're using the basic, assuming the linearity assumption, R squared 62%, which is quite large. But to get to the second question is whether or not since the answer to this is yes, the second question is like, well, did they drop consistently for both charter and traditional public schools? And this is an example where I think looking at the residuals beyond model checking could be useful, right? So the first thing I'm going to do is pull out the residuals from the regression model, and I'm going to create two new columns in my data set, one with just the residuals and the residuals log, which is simply the residuals from the logged transformed model. And I'm going to, here I'm just plotting, I'm doing a density plot, which is like a histogram, except it smooths it out. And I'm color coding it by charter school. So right off the bat, I see something, right? So I see the traditional public schools, the residuals seem to be shifted, higher a little bit. So the residual is a little bit more negative for the charter schools, and that pattern holds for sure, looking at the residuals from the log transformation. Right. And so I can then do a null hypothesis test on my residuals here. And so I'm setting this up such that my null hypothesis is that the residuals between charter and traditional public schools are the same. And so if they're the same, that means they dropped in the same pattern. If they're not the same, if the residuals are not the same, that means charter and traditional public schools dropped differently, right? Such that, what we're going to see is the residuals are more negative for charter schools, which means they dropped more than what the model would predict, right? Which is sort of, an interesting data point in sort of the context of the charter school debate in the country, right? So then the alternative is that they did not drop in the same predictable fashion. So here I'm just doing the t-test where my dependent variable is the residuals, and I'm modeling that from the charter school indicator. So we end up with a statistically significant t-test, right? And so these are the means for the false group, which is traditional public schools, and the traditional public schools, where essentially what we're saying, what this confidence interval here is that we're 95% sure that charter schools passing rate dropped between 6 and 11 points more than their traditional public school counterparts, right? So in other words, if the traditional public school dropped by 10 points, the charter school is going to drop between 16 and 21, or I guess that's almost 22 points or percentage points, right? And so at the time, this was kind of an interesting result. We could do the same thing with the residual logs, right? And so another question is like, why am I doing this both ways? Because this is easy to interpret. This is percentage points, But now I have a confidence interval. I end up with the same answer in terms of I'm going to reject the null hypothesis, except now my 95% confidence interval is in log odds, which even for me is super difficult to interpret. You have to take an anti-log to get it back to your raw metric. And so if I'm having a hard time thinking about it and explaining it, trying to explain it to a layperson or a policymaker is hard, which is, to say I wouldn't necessarily do it, but this gets to that in a reasonable way, knowing that this again is going to be a conservative estimate of what the real difference is. Questions about that? All right, so I'm not going to say a whole lot. We're not going to go into the level of detail of fitting, but fitting polynomial models, and in this case, we're going to try to fit a quadratic, right? So we looked at y equals mx plus b. If you remember, sometime probably in algebra, you also had to do parabolas. And actually, we looked at parabolas in terms of the ordinary least squares. We looked at the sums of squared residuals. It turned out to be a parabola, right? Those things it's a fairly common occurrence. So all we're going to do, right, if we want to fit a quadratic, is we're just going to add in this square term. So we're going to have a new coefficient. And in some ways, we're kind of stepping towards multiple regression, which we'll do formally next week. But we're just going to add in this square term. So we're going to get a new coefficient. To do that, there's this function in R called I, which is sort of for the identity. And I'm doing this because I'm doing the squaring kind of in the formula. So this is just saying square it before you pass it into the regression equation. So I'm adding in the pass, and then I'm keeping the linear term as well. So I have a quadratic and linear term. And to give you a sense, right? So by doing that, I actually increased my R squared to over 70%, right? From the 62%. I think looking at a picture, here's the summary output. So we could see, here's the square term, right? So that's this coefficient. So it's like a slope, but it goes in front of the a squared. And then we have the slope in the linear direction. And you can see here is our R squared. But I think looking at a picture helps a little bit better. So what are we doing? So this was that original linear regression. We're trying to fit a straight line. But hopefully you can see, as I see, there seems to be a natural bend, right, in the data. And so by adding in that square term, we're allowing the line to kind of bend in that quadratic, that quadratic sense. So we're, I don't actually have a good plot here, but visually just try to imagine if you're trying to draw, a line from each point to the regression line, right? I have many shorter lines going to this quadratic than this line, right? So for the straight line, all of these points down here, have to go further, which means the residuals or the squared residuals are going to be much larger. Okay. Well, we could go crazy. We can add a cubic term, right? So that's this purple line. So you could see by adding the cubic term, right? So if you remember, let me do a little bit of drawing. Don't do this too often. So yeah, here, draw, right? So, right. So quadratic terms are going to look like this. So quadratic terms are going to have one minimum or maximum. So this is positive quadratic, and this would be a negative, right? When you have a cubic terms, they're going to look something like this, where you have one minimum and one maximum, right? Hard to interpret, and probably a phenomena that you don't see very often and actually in practice. But by doing that, right, we can see up here, it does okay. It's kind of the same, but it allows the regression line to kind of get these points down here. There's more points down here, but because of the way the quadratic, this kind of has to flare up because we don't have the term to allow for that additional bending, right? So we do increase the R squared. We go to 71%. What did we have before? So on the quadratic, we had 70.6. And so by adding the cubic, we go to 71.6. We add another percentage to our R squared. It's something, but it's not a lot, right? And so you're gonna probably encounter this many other places in the program, particularly if you take the predictive modeling courses is you kind of got to find this balance between overfitting and underfitting, right? And so Chris Albin, I think I love these kind of plots, right? So the problem with overfitting, and like I said, we'll talk about this in a few weeks of how we evaluate models from a predictive modeling point of view, is that our goal is often to generalize or make predictions to new data sets. And so if we overfit to the data set that we have in the training step, right, is generally going to be really sensitive to that data, such that new data that may be slightly different may end up with bad predictions. So overfitting, like, you think, oh yeah, making my error smaller, but it means that if the new data has even small amounts of fluctuation from what we actually observe, those predictions become bad, right? So this would be an overfitting. I would say doing a cubic in this is overfitting. And I like this one on the right? So this is way overfitting. So we're trying to get these reds. And you can underfit, right? So just doing a straight line. So, in this case, it's probably like a quadratic, which is sort of ideal, sort of a nice balance. You may ask, there's a bit of an art here in deciding where that is. And so as you learn about validation procedures in the upper level courses, you'll kind of start to learn some metrics on how you find that, that balancing point where you have a sufficient fit to make good predictions going forward. One other way you can do that is like, how did I decide on quadratic? Well, I've looked at enough of these, but there's something else I like quite a lot in R, and that's, it's in other things. It's called lowest regression. And it's a way of doing localized regression. I actually have a Shiny app that kind of depicts what's going on here. So what lowest regression is going to do is it's going to try to find different estimates as you go across the range of your independent variables. And it's essentially going to estimate lots of small regressions using weights based upon how far away you are. So here I just have a quadratic function that I have some random noise. And so what we're going to do is we're going to start at -1 because that's the lower bound. And so we want to find out, where we would predict at -1. And so what lowest regression is going to do is say, well, let me look at points around -1. And the closer they are to -1, the more they're going to use. As I get further away, I'm going to have some parameter called span, and I'll get back to that in a second. So, so these white points are going to be weighted less in my regression to the point where I get to here, these open points. These points aren't even being considered at all to estimate this this regression. So for this orange dot at -1, this is where I end up. I'm estimating this linear regression, right? So I have a degree, right? And so if I animate this, you can kind of see how lowest is going to go across, right? So you see how the slope is changing as we move. So now we're not using any data over on the left, and as we move right? So we're just essentially estimating a whole bunch of them. And this will go back, and what we can do is say, we can kind of, keep this. And so that orange line is going to be the final lowest regression. So it's kind of an algorithmic approach as you go from left to right. Now, let me pause this. So when we think about the span, let me bring it over here. Right. So if I increase the span, oh, I got to show the whole lowest. I'm not seeing it. Is it changing? Oh boy, I was fixing it earlier. I don't know what happened to it. All right. Well, or do I have to redraw it? The span's not changing. So the span is a parameter that has to do with how far away from the point. So the bigger the span, usually if you get the span close to 1, you end up with the linear regression, but it looks like my span parameter is not working. And I don't know why. So sorry about that. Then the other thing, right? So by default, right, this is linear. I like to start with linear, right? Because we can see, all right, I muted too. Okay. We can, we've talked about linear regression. What Loess will do, like there's a function called Loess in R, will actually fit local quadratic functions, right? And so that's gives you a little bit better, just so you know. But if you look at the parameters in the function, that's what you're actually going to get. Let's look at cubic, right? So if you're unsure, right, Loess is going to find those bends sort of naturally for you. So it's a procedure I like quite a lot. And then this is actually Old Faithful. This is I'm trying to remember here. On the x-axis is time between eruptions, and the y is the height of the eruptions or something like that. I have to go back and look at the data set. Actually, is it here? Anyways, questions about this is kind of a really, I think, useful tool to have. And I think in the slide deck, well, I'll show you how you can run that. And then there's an article if you want to read in longer form of how this is working. And if you want to go into the mathematics, how the weights are actually calculated at each step. Oh, it is waiting time and the eruptions as you go through. So there's a little bit written text there. Now, if you really want to, if you're interested in the New York City's or New York State school stuff, let me open this up. I had to stop the other shining up. Oh boy. Oh, I'm missing a package. Sorry about that. Oh, no. Well, it's not going to run. Great. You can run this. There's a GitHub repo. This will give you a sense of the years, 5 years. I made some updates. You can run this if you want to explore that relationship. So I give you the ability to look at ELA and math in grades 4 through 8. So you can pick years, but it's pretty consistent. Doesn't matter what school year you look at. You see that relationship. So that's regression, kind of hopefully in enough detail to give you a good understanding. And even as you get more into the more advanced predictive modeling, a lot of them really rely on some of these concepts that we did in the last couple of weeks. We're going to extend it in 2 weeks to situations where we have non-normality or data that don't fit normality, right? So for now, when we talk about normality assumptions, and the textbook talks about it, I just want to reiterate what we're talking about is that we're assuming that the residuals are normally distributed, right? That's key. And so in 2 weeks, we'll encounter data where those residuals are not normally distributed. They might follow some other distribution. And so we'll move into other types of regression models, kind of generalize that normality piece. Next week, we'll talk about multiple regression. But if you have a good grasp of this, really the key part that we'll talk about next week is how to redefine R squared when we can't take a correlation squared, because we only correlation is between 2 variables, and we're going to add a second predictor, or a third, or a fourth. And so we don't really have a overall correlation coefficient. And so how we calculate that's going to be a little bit different. But let me pause, see if there are questions. How are we feeling about this?
So is the lowest, I guess, modeling scenario, is that similar to how like a machine learning model would run linear regression or multilinear regression, in the sense that it's looking for local and global minima to define the curve?
It is one approach, but it's not, I mean, if you not, well, I don't know. Do you want to take a stab at this, Angela? I don't, I will say that it's a step in the right direction. And so far as it introduces more of an algorithmic approach to solving the problem, where if you think about ordinary least squares, is very much to me an algebraic approach. So I'm going to use 2 new forms. So there's when you get into advanced modeling, you're going to find out that there are what are called closed form solutions, meaning there has to be a solution. So ordinary least squares is closed form because in essence, we're trying to find the minimum, so there's some function that defines the residual sums of squares. And there has to be a first derivative to that functional form of those, right? We saw that. So it's closed form because there is a solution. There is a single solution. If you have that functional form, there is going to be a derivative. Then there are non-closed form where we're going to algorithmically try to find it. And I'm going to show an example in 2 weeks of like kind of what I'm talking about. And in those situations, there may not be a closed form, right? So it may not, given certain data, it may not be able to find the minimum. And so it just keeps going. And and so those kinds of models error out. I mean, it's unusual, but it's important to know about that. So lowest kind of fits somewhere in between, in my view, right? I like it because it's closed form given certain parameters like span and the like, but it's not like there's a single formula that we're finding the minimum. We're just estimating lots of models, right? And so that span parameter is saying, well, how far we go. So we could get different solutions given different parameters, right? And that span is really going to determine whether or not you're overfitting or underfitting your data. But to me, the point is I'm going from left to right and just kind of algorithmically determining where my predicted value would be given some algorithm. Now, in this case, the algorithm is just lots of little regressions. But in 2 weeks, we're going to look at situations where the algorithm is a little bit different. We're going to use different types of numeric optimizers, which I won't talk about how they work because, quite frankly, I'm not a computer scientist. So I don't know how they work, but I can see how they're working. And I think hopefully that's sufficient for you guys. You can kind of get a sense of what's going on without knowing exactly how it's making the decisions. But yeah, I wish we had time to talk about classification and regression trees because that is the next step. Because that's an approach where we just keep partitioning the data. And at each partition, as we get smaller and smaller subsets of the data, we're going to use an algorithm to try to, figure out the best way to partition the data. And I like them a lot too, because they're non-parametric methods. And when I say non-parametric, I mean there is no assumption in the distribution of residuals, right? So using that with a regression, which is parametric, so parametric just means there is an assumption of some kind of distribution of the residuals. We've only seen normality so far, but we'll see others soon, right? But there is a defined, distribution for the residuals. The non-parametrics just don't have that. Doesn't matter. Doesn't matter what it is. So I usually do them simultaneously. Now, in Angela and I's work in sort of educational psychology, educational research, social sciences, I don't see those kinds of models in journal articles very often. People still just do regressions, multiple regression and logistic regression. So it tends to be what we report, but I generally run them behind the scenes. And then when we do, we have a book chapter we published last year together on predictive modeling or predicting student success. Again, we tried a bunch of stuff, but we ended up just reporting random forests because the random forest models outperformed everything else in all but one case. And so for simplicity, we just used the one modeling approach. But anyways, I digress.
I guess one other question would be, I work in finance, so I feel like I would have to log things a lot in terms of normal data. So I guess the question is, if you're finding it hard to interpret, what do you think is the best approach to make it more interpretable? If you have to take that approach, depending on your distribution.
That's a good question. We have a finance course in the program.
I have a lot. I have too many questions for electives. I have to figure out which I'm.
Honestly, I don't know. I don't know, Josh, because I don't. I might reach out to like Arthur because I think his pre-academic life was in. I think he worked. I should know this. Morgan Stanley or one of those kinds of companies. So he. I don't work with those kind of data very often, if ever. And the skewness I see is generally only like because we have some kind of, household income in our model. So it's really not, it's like one predictor of many. And, we do the log transformation. We don't really worry about it. This also goes to something we're going to talk about in a couple of weeks is, up to now, we're kind of teaching this from a more traditional, statistical point of view, where we're talking about inference, right? We have a data set and we want to try to infer something from that data set. We see predictions, right? Because we're using predictions to get residuals and the like. But we're not really predicting to new data sets, which is kind of how data scientists kind of handle this problem. And when you move to that framework, a lot of times you do the log transformations in your independent variables, but you don't have to interpret the coefficient. You just need to know that it's correct, right? So the know that the slope is is specified in log odds doesn't really matter because you're going to get a prediction out on the other side. It becomes a problem if your dependent variable has to be log transformed, because then you have to do that extra step. But if your dependent variables can stay in the original metric, then you're going to predict a yes or no. And that's what we're going to do in 2 weeks, right? Where you're generally going to have a dichotomized outcome. And we're going to care a little bit less on the interpretation of those. So that's one way I would think about it. There's also another concept, and this, I probably should talk about this next week after multiple regression. The interpretation of the coefficients, in this case, slopes, as we're calling them, but we're going to call them coefficients starting next week. The magnitude of them is a little bit problematic to interpret, because there's this notion of fungible weights where, when we go from what we've been talking about in the terms of closed form, right? There's a single solution that is going to minimize the sums of squared residuals. Let me go back to the slide deck from last week. So what I'm talking about, okay, right here, we want to find the slope that ends up with this sums of squared residuals, right? And this is in a single, but next week we talk about, if we have two predictors, we're essentially, I showed that, right? We're trying to find the bottom of sort of a bowl, right? So we're going to have a parabola in 2 dimensions. Okay. And when you add more and more predictors, right, we're still trying to find the minimum, but it gets a little bit harder to visualize because we're in, greater than 3-dimensional space. Yeah, 4-dimensional, right? But the idea is we're trying to find that minimum. Okay. So this notion of fungible weights is to say that if we relax that to say, well, we'll accept a less than optimal minimum sums of squared residuals, like just even like a fraction of a percent, right? We can this point is acceptable, and this slope is acceptable, or this this correlation is acceptable. This one's okay. We could see our correlation can fluctuate a little bit here, and and you see the sum squared residual is not getting a whole lot bigger, right? Such that on this visualization, it's hard to see that these points look like they're on the pink here, right? All right. So if you can imagine, if you have a lot of them and you allow just a slight variation in, that minimum, you can end up with infinite number of coefficients that would fit, that could be used to get that same sums of squared residuals, right? So that's what we mean by fungible, right? So the weights, or let me just be concrete about it. when we say, these, which are slopes, and here now we have an intercept and we have two slopes, right? And when we have more of those, we could change these up and down in different combinations that would result in the same sums of squared residuals, right? And so what happens is interpreting the magnitude, in other words, the size of these, becomes really problematic and really sensitive to your data. But interpreting the direction, in my view, is totally okay, right? So it doesn't really make sense because we're talking about, but like you can have some coefficients that are positive, which is to say, as this coefficient increases, my dependent variable increases. If they're negative, you're saying as this variable decreases, my outcome increases, right? So the really up and down relationship is negative. So the direction is okay, but the magnitude, meaning how big that is, becomes really problematic. So anyways, there's a paper, it was in Biometrica, if you're so interested in the details. If you Google Biometrica fungible weights, it was from about 2012 or 13 or something. But it really, it didn't get as much press as I would have thought, maybe because Biometrics is it's a top tier journal, but it's read probably only by academics. But it kind of casts doubt on a lot of these models in terms of generalizability. And that's, anyways, and you go through, when we talk about how you evaluate models from a predictive modeling point of view, we're going to try to take some of that into account. Okay, Crystal's asking, I think if you can do this, the regression lab is due this Sunday. You didn't have anything due this week.
Actually, it is due the 13th. There are, according to the course.
Okay, that's fine. I'm going to be busy grading proposals, and I think Angela's busy getting caught up. So that would have been wait, the 13th. Wait a second.
Yep.
What's going on? So we're November 2nd. Oh, I see. Okay, whatever.
After multiple regression.
Yeah. If you need the time, go for it. Because we need the time.
Can I ask another random statistics question? It has nothing to do with regression.
Yeah, go for it.
For example, like if I'm looking at 538, which I often do read, right? I like to do like Monte Carlo simulations. Like, is that statistics? Is that predictive modeling? Like, where does that fall within the?
So Arthur and I always joke about this. Data science is statistics.
Right.
So it's statistics. Yeah, he does. Yeah, so Nate Silver does a lot of Monte Carlo and a lot of Bayesian kinds of things. And we'll do Bayesian at the end, a little, or at least conceptually what it is. I have to, I was a big fan of Nate Silver. He came up something super clever. However, I don't know if it's any fault of his, although I've noticed he's becoming increasingly how do I put this, condescending, and his head is bigger than maybe it's currently justified. I don't think his models are quite as good as they used to be, in part because the polling models are now, I think, influencing how people respond to the polls. So,
There's
taking
an inherent bias that.
Right. And I think some of these things, and the way that the 538 writes about particularly political polling and political predictions, is starting to actually influence the outcome of those elections. So
right, because it's not as fringe anymore, right? It's much more mainstream in the sense that like people are looking at that and saying this is reliable as the prediction, which maybe it is or it isn't, but like for example, 2016, right? In terms of like the forecasting for Trump. And I guess it's like people have a hard time thinking about it probabilistically. but I mean, I think they do a really good job with visualization.
Sure. Yeah. Yeah.
Statistics that I think is for mainstream sources is good, but
Mhm.
yeah.
I just think there is, I think there's some influence, like some violations of independence assumptions, right? Potentially is one way to think about it, that they're not really acknowledging is I think he thinks of himself as a benign bystander, just observing what's going on, and isn't acknowledging how, if not 538 models, every other news industry is trying to replicate what he's doing, is having an impact on the data that is being collected. Like I think there are social scientists I've seen references to papers. I don't read them. This is way outside my expertise. So I'm talking a little out of turn right now. So I'll say that up front, but um, we know that the response rates on these polls have been changing over time. They're also abysmal, in terms of how many people they actually have to call to get the 1,000 or so that they need. And then and for a long time, right, they didn't call cell phones, which means until recently, I never got polled. I do now because they'll do it through text and they'll call cell phone, but that was only very recently. So there's a bias in the sampling. It's not really a population sampling. It's something else. And we know that some people just answer not what they really think, and they try to throw pollsters off because it's become such a big business, right? So those are all, measurement error problems, and we don't talk about measurement error. And anyways, I digress on that, but does that make sense? Like it's
Yeah, no, I guess I'm just wondering, like, is there a realm of statistics that I should explore? Like, I know you're more an academic focus, but I guess like if I'm more interested in, let's say, predicting like NBA results, like, is there a realm of statistics that I need to explore to be more well versed in that? I guess is my point.
No, I mean it's all related. So if you do statistics, and so until recently, anybody who's had a job title of data science probably had a statistics degree. Like data science degrees have only been a thing for the last 5 or 10 years, right? I think so. This is going to date me a little bit, but like when I was doing my undergraduate, computer science departments were new. Anybody who was doing computer, like when I got my first job out of college, the vast majority of my coworkers who were writing software had degrees in mathematics, not computer science, right? So computer science broke out as a separate field from mathematics, which is where a lot of research was done. And if you look at the 60s, 70s, 80s, like AT&T Bell Labs, where S was created, which is the predecessor to R, for example, they were all mathematicians and statisticians. And then, data science kind of broke out, so data science is kind of breaking out of, I think, statistics. And for a while, statistics wasn't really its own field separate from mathematics. Like in my undergraduate program, the statistics was taught within the mathematics department. There wasn't a separate statistics department. So these things kind of branch off and grow. So anyways, I think it's all the same. What I would recommend is, like, Angela and I are doing an independent study with 5 students this semester, and we're going to give a talk probably in January, kind of as a review of what we're doing. And what we're doing is building an R package that will look at, in fact, we just looked at now, we have almost 100 different predictive models, and we have about 50 data sets right now, and that will grow to, and then we got a framework to add more. So what we're going to do is look at all of these predictive models across all of these data sets in order to see how they perform relative to one another across different data sets, not just in terms of accuracy, but in terms of performance, time, and the like. So that, hopefully will be an interesting way to look at it. Like, how different are all these different procedures? This is predicated on a paper that was published in 2012, kind of in some ways redoing it and trying to enhance It was called, Do We Need Hundreds of Classifiers? So they only looked at classification problems. And what they found is, yeah, there are all these fancy methods, but, 8 times out of 10, random forest is going to be the better performing model. So do we really need all of these sort of modifications? And so you learn how random forest works. And, oftentimes that's what I do. I just move on when it's not like a critical thing. But if I'm doing finance stuff or medical, I might care a little bit more. Right?
I don't know.
Go ahead,
I don't know
Angela.
I don't know if this answers your question, Josh, but one of the things that Jason and I talk about a lot is for statistics, it's not only just generating results, right? It's being able to interpret the results in the context of what we're examining. And so that is actually a hard skill to have, and having research questions or having something to guide our analyses or our process. So it's not just blindly going into data and doing whatever until we get a number we want. It is going into this process with reason, and then being able to explain it.
Intentionality, I would say. Yeah.
So that whole process is a skill, I would say.
I think finally I get the sense that, for a while, data mining was a big hot phrase in the field. And I think we're starting to kind of shy a little bit away from that. And so, I mean, you'll still see it, but at least in the education world, right? It was like, well, we have all this data. Let's mine it to find insight. And
Like neural network, more or less.
No, we're just going to look at all these variables and how they're related to student success, right? And if we go back
not
to
really a research question in mind, just like
there's no, yeah. Let's just see. Let's just find patterns in the data, right? And type 1 error rates apply regardless of your statistical model, right? We learned it in certain contexts here, but there's always type 1 error rates. And as we showed, right, if we're using 95% confidence or 95% confidence levels to decide that this is a meaningful relationship or not, and we look at 20 random relationships, well, one of them is likely to be significant. Right. So there's this notion of practical versus statistical. And it gets worse when we talk about data sets that are really, really large, because, hopefully you see, right, when we calculate that confidence interval, we have n in the denominator. So as n gets bigger, that ratio is going to get smaller, right? Which means we're going to, even if the estimate is not far from 0, the confidence interval is just going to keep shrinking until it doesn't overlap 0. And then we say, hey, we have a significant result. Is that meaningful? Is that really meaningful? And that's to me, what data mining was. I don't think people are quite going there, right? Just let me, then there's unsupervised, right? Where I just want to find pattern, or I'm just going to take the correlation between every variable and every other variable, which is sometimes useful, right? And you can create these really nice correlation matrices. And I'm just going to oh, here's an interesting one. And it's like, what is it? Then you end up with things like, oh, there's a correlation between ice cream sales and crime. Right. Which is a great website, by the way. Spurious correlations. I think I probably spelled it. So we have suicides by hanging, strangulation, and suffocation. So oh, here we go. Nicolas Cage films and swimming pool drownings is correlated, right? So if you do data mining, these are the kinds of things you can come up with. Cheese consumption by bedsheet tanglings.
What even is that? I don't even know what that means.
I don't know what that means either. So margarine consumed is correlated to divorce rates in Maine.
I just put a link inside here because this reminds me of the book on how to lie with statistics.
Oh yeah,
which is it's like this very thin, great book on, and there is a one where they kind of go over correlation between smoking and college grades and like how you can create that correlation, but is it a real correlation? And it's a fun little tiny read. that I recommend everybody just have fun with, because
Yeah.
yeah, I mean, it's what kind of drives, if you see salacious headlines of where maybe like some data or some predictive models don't seem to make sense, some of it comes from these kind of picking and choosing of data points that then argue significant arguments that people start buying into if they're not skeptical enough. Maybe
Yeah.
that's why we have to remain skeptical.
Yeah, one of
Always.
my favorite books that I love to recommend is Innumeracy by John Allen Polis. This is also another short book. It's old by this point, but it is so relevant. I think he also wrote how he's got Beyond Numeracy. Oh yeah, How the Mathematician Reads the Newspaper, also very good. But innumeracy, as he defines it, is you can think of it as a literacy, right? What a literacy is to reading, innumeracy is to numerical understanding, or numeracy. So, anyways, there's a lot of people who are writing about people's lack of quantitative literacy being related to making all sorts of bad decisions. I mean, if you walk into a casino with the expectation that you're going to leave with more money in your pocket than you come in, is a significant failing of schools teaching numerical literacy,
Yeah.
in my view. If you're going to go to have fun, great, have fun, but you're going to leave with, less money.
Okay.
Anyways, yeah, these are all fun little things.
Put that on my Goodreads. Thank you for that recommendation.
Yeah, it's short. Oh, and then let me recommend too, for because I don't think I recommended this in when we talked about ethics a little bit. So mathbabe.org, you can go here. But Weapons of Math Destruction is a fantastic book on ethics around data science and the like. And there are a lot of them. I kind of like her approach. She tries to have a little bit of fun. Some of the chapters are more serious than others, but some of them are really interesting. Like there's a whole chapter on the U.S. World and News college rankings, and that's what I think about when how what Nate Silver and 538 are doing might be influencing politics in potentially a negative way, right? So what she outlines is, if you don't know U.S. World and News, they rank undergraduate colleges, and a lot of people use them to try to decide where they're going to go to college. A lot of teenagers, right? It doesn't work. There's actually an audiobook. I actually listened to it on a ride once. I'm sure it's on Amazon. I can find it in a second. But anyways, she outlines how it turns out to get high on the rankings really boil down to selectivity. If a university had more applicants than they accepted, they were higher ranking, which is why the Ivy Leagues were always at the top. And a lot of applicants and very few of them are accepted. But then she outlined and she showed instances where universities and college started to manipulate their acceptance rates as they started to figure out that was an indicator of, or having whatever lower acceptance rates would boost them up on the U.S. World News, and just for decades this has kind of been a problem in higher education. So imagine that, right? So that parallel, now you have 538 that are making political predictions at a time when it was just sort of observing data, but now people are aware of those models. And so it's actually changing reality, I think, in a way that I'm not sure they're keeping up with. All right. Wow, we went way off topic.
That's my fault. I
No, I love this. This is great. But this is fun. Yeah, I hope this is valuable for those who stuck around. But I'm glad you're thinking about these things. These are great things to think about, talk about, and yeah.
I'm kind of interested in doing a study on like steroid use and athletic performance. Any ideas on where I could find a data set like that? I was really inspired by Icarus, the documentary.
I haven't seen that. Is that
so interesting?
Ooh,
What's
maybe
it
you
on?
It's a
could look up.
documentary about a bicycle rider. I mean, he's a bicyclist,
Oh,
but he's
okay.
also into documentaries, and he wants to see the effects of steroid use. So
Oh,
he gets the guy that does the Russian doping. That he did it for the Olympics, to see how that can impact his performance. And as he brings him over, like there's a whole bust on the Olympics committee. They find out about what the Russians were doing with doping, and like the Russians try to get this guy
Yeah.
because he was the
Oh.
leader.
I may have a suggestion only because me and during the boot camp classes, we're looking into baseball statistics, specifically during the time where steroids was rampant. And I was talking, me and my husband was talking to see if old baseball statistics, especially when it came to batting averages, would be different compared to the time when doping scandals were happening. So maybe.
yeah. There's our packages to get baseball data directly. So I don't know them off the top of my head. There's actually, I think, a book using R for sports. I might be baseball specific.
Sabermetrics, maybe. Yeah.
Let me actually just go to Amazon. Oops.
Yeah, because I'd love to see that, because me and my husband were literally talking about that as we were going over the statistics, because God.
Yes. Analyzing baseball data with R. There's
Perfect.
a whole book. So I knew there was. So that would be a good one. I used to be way into baseball when I was a kid. And again, this might date me. I had tickets to see the Red Sox Yankees in Fenway Park the week after the strike started in the 90s. And then I never came back to baseball after that. I was so pissed. But I just saw, right, didn't somebody get more than 61 home runs this year?
Yeah,
So,
Judge. No. Yeah,
what?
he beat
Yeah, from the Yankees.
Yeah.
Aaron Judge.
But I remember just the tail end, like there were I forgot his name.
Wire.
Yeah, who got 70 some on, and
Yeah,
right?
I think
And,
Bonds has the all-time season record, but he doped, so
yeah,
that's-
so that they don't count it anymore, right? Or did they put an asterisk next to his name like they did?
I don't know. I don't think they put him in the Hall of Fame, but I don't know actually. I don't follow baseball anymore either. But I guess that's the thing. If you were to do a statistics test on like home runs, like difference in home runs, I would be shocked if you didn't see a difference between those like pre-standard doping, which I guess is like 90s or 80s, but
Yeah.
Yeah, I think when I looked into when I was looking into the analysis, the best hitter was Barry Bonds, and I don't even know if he's like on, like I didn't know. Of course my husband knew right away. Who he's like, yeah, probably you'll have Barry Bonds as your top guy.
Yeah.
yeah, because he initially was pretty skinny and then he really like got built out, but
yeah. I mean, there's literally a YouTube video about how Barry Bonds was so good at hitting that he didn't even have to use a bat to hit. They found out statistically, like that he could just come up to them and like they wouldn't even try to. I don't know. The statistics was really great. If I could find the video, I'll post it on Slack.
Yeah. Send it on Slack. I would like to. Oh yeah, look at this. During his 10 years, he did not receive the 75s to get into the Hall of Fame.
Oh wow, yeah.
yeah, I think they're punishing him because of that, but I don't know.
Well, I thought it was interesting that, and I saw the articles, the headlines. I didn't really read through. It's like, breaking the, was it Maris? No, it was No. Who wrote the record?
I know it was 61. That's it, because it was
Yeah.
in New York news, but
And I watched the documentary or movie on HBO a long time ago. Billy Crystal, I think, directed it, right? What was the 61? I think it was a movie, or was it a TV show?
yeah, you're right. It's Roger Maris.
Roger Maris. Okay.
It's
And
interesting because in the documentary,
here's
the guy was doing like a Tour de France or whatever, or one of those races,
yeah,
and he wasn't able to get like significant improvements in his time. So I'm like
I
curious
saw
about
this
like,
other biker that like they did a documentary on him, and he like talked about how steroids really improved his biking performance.
yeah.
but-
It was a guy. Well, I can't remember his name. I think he had just cancer of some kind.
Well,
oh, Lance
that's
Armstrong.
Lance
but
Armstrong.
there's other guys like biking has also had its doping issues as well. But
Right. Didn't Lance Armstrong test
no, he
positive?
did. But I think
Yeah.
there's other people. Like he's the most well-known American, I think.
Okay.
But and
They
also
show how they cheat the system. It's really interesting.
Hmm.
yeah,
Yeah,
I would say you would focus on
yeah.
a sport, maybe like focus on baseball or biking,
Yeah.
and you would find more documented cases of steroids, because I don't feel like that's like a clear data set. But like I think baseball released a report of, let's say, 200, 300 names of people
Yeah.
that they suspect with doping, and then you create your own flag with like generic baseball data. But
Yeah, that would be. Yeah. Yeah, you
Yeah,
could.
I found the video. I'm gonna still put it in Slack so it's there.
Thanks. Yeah, I opened it. I'll watch it later.
like if you use like a cricket bat,
No, like absolute just nothing. If he just went up to the
like his
bases.
hand,
No, just his intimidation alone. They were
Oh,
scared of
because he
him.
would get walked.
Yes, that was exactly.
Oh, that's like the Billy Bean value of
Mhm,
walks.
Yep. And even the guy at the end, his analysis kind of, you could see that he's startled. He's like, what? That was right? What? So it's a very good, fun video to watch statistically.
Thank you. I will.
Thanks for the suggestions. I might tackle this. I'm not sure.
Well, I don't know if I would recommend it for this course, but you got to
You
do
have
a
time when
capstone
you're
at some
working
point.
and in school.
Yeah.
I don't have time to be doing maybe my December,
Lot of
January
time.
break. Yeah. Props to you.
But thanks for the ideas.
Yeah, like there could be well, yeah, I mean, well, Nate Silver, that's how he started, right? On sports stuff.
Yeah, I think he was initially based off of New York Times, but
Yeah.
yeah, because it was like I went to University of Maryland. It was like a Maryland freshman book. That was my first introduction to Nate Silver, and then
Okay.
like but again, he's gotten a lot more mainstream since then. But
Oh yeah. Yeah, well, what was it? I don't remember. Was it 2004 or something that he?
yeah, because he used to be a KPMG consultant, and he was really bored. But I think he had a statistics background.
Yeah.
But I've always like, that idealistic, like I was at KPMG. I'm like, oh, I could be like Nate Silver one day. But who knows?
Yeah. Yeah. So yeah, well, I think what he did was super clever by pulling multiple polls. Very, very clever. And then weighting them, right? I think that's the other thing. It wasn't just pooling it, but he had historical data and said, well, these pollsters tend to be off this way, and these are off this way, and you can correct for it over time. Just super clever. All right. Wow. I'm going to stop the recording, but this was great.